So, we have been looking at the first law of thermodynamics and what is work, what is heat, so heat as, and both of them are some kind of one way. I mean, either I can put in heat or I can put in useful work, right, to change the energy of the system, internal energy of the system. And first law says the only way one can change the internal energy of the system is by either doing work on the system or putting in heat into the system. Okay. So, they are two different eyes of the same person in some sense, right, or two different sides of the same coin, the heat and work, right, and the coin is energy, the coin of energy, right. So, first law of thermodynamics tells you everything about energy audit, right. The only way I can change any internal energy of any system, and this is a useful way of detailing first law of thermodynamics, is so the only way I can change the internal energy of the system du is if I put in heat into the system, which is dq, or the system does work on something else, that is how I am removing the energy, right. So, that is minus dw. Okay. So, this is a useful way of understanding first law of thermodynamics. There are other statements that says energy of this universe is a constant. All these things are identical statements, but they do not give you this kind of a physical insight, the useful physical insight which is used to then solve problems and then build your engines, Carnot engines and things like that. Okay. Okay. So, then what comes after the first law? Of course, it is the second law of thermodynamics, and this is the most important law of thermodynamics. It introduces, so even for the material synthesis processes, second law of thermodynamics is what defines certain potentials that and then certain equations that allow you to grow these materials, right. But before going there, so second law of thermodynamics first in its basic form introduces the idea of or it does not really tell you what this concept of entropy is. Second law of thermodynamics is quite agnostic to what entropy is in a very physical sense, but it tells you a recipe to calculate entropy changes, right. In fact, you must realize that second law of thermodynamics came before Boltzmann gave the definition of entropy, right. So, now very quickly, right. So, Boltzmann said that entropy is defined as K ln W, where W is the number of microstates in the system. So we have to count the number of states in the system, and if system can access all these states, then it has a larger entropy. If system can is not able to access all these states, system accesses only much less number of states, then it has lower entropy, right. So it then becomes a problem of counting, and then this is what you start StatMech with, right. So, by defining what entropy is, right. But thermodynamics does not care. Thermodynamics is saying that all right, well, and thermodynamics came before Boltzmann definition of entropy. Thermodynamics sort of realizes that there is something called entropy. It is a state variable, right. So, which means so if I change the system from one state to another state, it changes from one entropy to another entropy, right. But so if I bring it back to the same state, the entropy comes back to the same state, right. So, the entropy comes back to its initial value, right. So, this second law of thermodynamics gives you a recipe to calculate entropy changes. Once I bring the system from one state to another state, or once I remove the system out of equilibrium and put it back in equilibrium, right. So, what changes, that is the question, right. To give you a very simple example, right. So, let us take our favorite example of this sealed thing. Sealed box. This is sealed on the outside. Sealed meaning so it is not going to exchange mass or heat with outside. This is an isolated system, and in this system I have nitrogen, I have argon, I have oxygen, I have, what is the other gas that we said, let us say hydrogen. Okay, so I have hydrogen, right. Now I am going to take a hammer and I am going to unseal this, right. So I am going to take a hammer and I am going to just make a dent here, right. So, of course, once you make a dent here, once you start removing the internal constraints, Of course, there is going to be mixing of nitrogen, argon, oxygen, hydrogen, right. So, all these gases are mixing, right. If I ask you the question what is changing, what is the variable that is changing, right. Now, earlier so it is not really the temperature of the system, right. So, especially when it goes to such highly non-equilibrium state, we are not even saying anything about the temperature of the system. The energy, so nitrogen has some kinetic energy, argon has some kinetic energy, oxygen has some kinetic energy, the energy is also not changing, right. So, just by doing this process of breaking the barrier, the energies are also not changing. What is changing is this is all getting homogenized, nitrogen is mixing with argon, argon is mixing with oxygen, and everything is intermixing with each other. And so, nitrogen which earlier could only access, let me use this color, nitrogen which earlier could only access this volume is now able to access the entire volume, right. So, nitrogen able to access 1/4 of the volume after barrier breaking accesses the full volume. Or in some sense more states, more spatial states in that sense, right. So, these are less number of, the number of states that nitrogen is occupying now, right, after I remove this is 4 times more than the number of states, right, that nitrogen was occupying before. Nitrogen occupies 4 times or accesses more number of states than before removing the internal constraints. Right. Same with argon, same with oxygen, and same with hydrogen. They are all able to access much more space, right, many more states, 4 times more states than what was there before, right. So, overall, right, something has increased, that is every individual molecule is able to access many more number of states. So, overall what has changed is the number of accessible states for every species. And as per Boltzmann's understanding, right. So, now that we are in the we have the benefit of hindsight, right. So, now that Boltzmann has already come up with his StatMech definition of entropy, that means that the new state where all the atoms have mixed with each other, a new mixed state has larger entropy than the older state. Right. So, older state, what is the entropy of the older state, let us say. Again, I do not know by the time thermodynamics came, I do not know what entropy was, right. I knew entropy only after Boltzmann said it, but I know that the entropy of this system is changing, some property called entropy is changing, right. Now, thermodynamics gives me a recipe to calculate how much that is changing by, right. Now, we can write now so this is entropy of, entropy is addable, right, entropy of argon plus entropy of oxygen plus entropy of hydrogen, which is all dependent on the logarithm of number of states of nitrogen, number of states of argon, number of states of oxygen, number of states of hydrogen, and so on and so forth, right. But in the newer state, however, it has 4 times SN2 plus, sorry, plus 4 times SAR, each of them has independently increased by 4 times SO2 plus 4 times SH2. Although the net volume is the same, now every molecule is able to share the entire space, right. So, now because of that sharing, the entire entropy of the system has increased, right. So, that is nothing but 4 times old entropy, right. Not sold, but S old. Okay. So, let me just erase that and then write it S old. Okay. So, in this problem, right, so nothing else seems to be changing, but the entropy of the system has increased. Okay. All right. Now, let us give one more example. Okay. So, before actually stating the second law of thermodynamics, let us give you one more example, and this example is, now let me go to a closed system. Let me use a black pen or a red pen. Again, this is a system of, I have a piston, right, and oops, sorry, I did something. Right. So, this is a piston, this is vacuum, right, and this is, there are some gas molecules here. These examples you may have seen in your high school chemistry, or if you are prepared for JEE, so these are the sort of problems that you may have done, or any basic mechanical thermodynamics courses, right. So, this is some gas. Okay. Now, for this system I am going to do two processes. Process 1, break the barrier with a hammer, right. That is a sudden expansion of this gas into vacuum, right. So, that is expansion into free space or into vacuum, okay, a sudden expansion, right. Then process 2 is, do it very slowly, right. So, first I do some work, right. So, some invisible hand is doing work, right. So, that is, let us say this is my hand, let me draw my hand, oops, sorry, right. So, let us say my hand is green in color. So, an invisible hand is coming here and it is slowly pulling it out, right. So, slowly pulling it out, preventing it from completely expanding, right. So, because the vacuum is just going to pull it away, the piston, but preventing it from expanding, I slowly just pull it to this distance, then to this distance, then to this distance, right. So, I am doing this in a very sort of quasi static manner. It is not completely static, but I am pulling it, waiting long enough for all these gas molecules to rearrange themselves, then I am pulling it again and waiting long enough for making sure that all gas molecules come to some kind of an equilibrium and so on and so forth. Okay. So, I am doing this in a very slow way, right. So, eventually, right, so the initial state is this is initial state of the system, and the initial state of the system has a temperature, right. So, this is temperature of the system, A is my initial system. Okay. Let us say it has some volume, right, it has some entropy and so on and so forth, and so the B is the final state of the system, and in final state so the gas molecules are everywhere. I have some TB, I have some VB. So, these variables define the state of the system, the TBs, the VBs, SBs and so on and so forth. Okay. This is the system, right, but I said this is a closed system. Closed system means there is also a surrounding, right. So, surrounding also has some initial state, I am just going to say that is Ta bar, right. If they are in equilibrium, Ta equal to Ta bar, right, Va bar, A bar for surrounding, initial state, okay, and S A bar which also means surroundings, right, and B bar is again the surrounding final state. I am going to say T B bar, V B bar, S B bar. Okay. Quasi static slow way, but let us say this is done isothermally, which means I am not changing the temperature, right. So, I am doing work, but I am not changing the temperature of this ideal gas. Let us say this is an ideal gas. Okay. Okay. Now, the question is, right, in process A or process 1 where I use a hammer, this is my hammer, here is my hammer, let me, okay, so that is my hammer, let us say, and I suddenly break this membrane, right, to go from A to B, or surroundings is going from A bar to B bar, or system plus surroundings is going from capital A to capital B. Okay. So, what is changing, right? Of course, I said this is an isothermal process. So, T A is equal to, or T A is equal to T B, right. So, T A is not changing. Similarly, T A bar equal to T B bar, that is also not changing. Now, this is an ideal gas, right, and so the internal energy of the ideal gas is just dependent on temperature, right. If temperature is not changing, so from A to B, right. So, initial state to final state, temperature is not changing, or this is an isothermal process, and that means that internal energy dU equal to 0, right. So, there is no, sorry, let me write it as delta U equal to 0, no change in internal energy. And that is also obvious, right. So, because this is expanding against, right. So, how can internal energy change? Internal energy will change only if I do any work on the system or I supply heat to the system, right. Now, I just broke it. Am I doing any work on the system? No, I am not doing any work on the system, right. So it is just expanding against free space, right. So, it is the gas by itself is expanding against free space. So, there is nothing that is opposing it to do so that the gas does work on the piston or piston does work on the gas, right. So, nothing is opposing the piston from expanding into free space, right, or gas from expanding into free space. If there is no opposition, there is no work done, right. Also, everything is at same temperature, so there is no heat exchange, right. So, there is nothing to change the internal energy of the system. Okay. Okay, but then what is changing? What is changing is, of course, the entropy of the system in B, because there are more number of states, and in this case so more number of available volume is more number of states. I can just divide this into your Boltzmann microstates, let us say, is greater than S of A, right. So, that is happening. So, this is for the system, okay. And what is happening for the surrounding? For the surrounding, S of B bar is equal to S of A bar, nothing has changed for the surrounding, right. So, number of states in this thing has not increased or has not decreased, there is no exchange of heat, right. So, that I am going to increase the number of states in the surrounding, or I am not doing any work on the surrounding, right. Surrounding is as it is, as if nothing has happened to it, okay. It is only the system where the gas has expanded against some free volume, right. So, against some free space or against vacuum, okay. Now, if I look at the total entropy, S B of course is greater than S A in this process, in process 1. Okay. Now, let us go to process 2, which is a more quasi static process. right. In this process 2, what is happening, right. So, first of all I am actually doing some work on the piston so that the piston just does not expand, right. So, I am carefully taking it this way, so to this position and so on and so forth, right. So, I am doing some work on the system dW, and that is some PdV work, right, and PdV work, this is an ideal gas. I can calculate this, right. So, I mean, so this you may have done many times, is nRT by V dV, right. So, that is the PdV work that I am doing on the system, right, and eventually this is an isothermal process, correct. So, if it is an isothermal process, sorry, this is delta W, because it is not a path function, it is a path function, du equal to 0, right. So, or delta u equal to 0. So, the delta q in this quasi static process should be equal to delta W, right, and that is nRT by V dV. You can integrate that. I am not going to do this calculation, you can do it yourself. Okay. Okay. So, there is some heat that the system is either giving to the surrounding. So, there is some delta q is non-zero, it is the same as the work done, but it is non-zero, right. So, some heat is being exchanged between the system and the surrounding, right. Now, second law of thermodynamics says the change in entropy, right. So, now it is going to define for me a change in entropy of the system is nothing but the heat that the system takes in, right, divided by the temperature at which it is taking in that heat, right. So, or let us define it in terms of ds is equal to delta q reversible, that is you have to do a reversible process, right. So, this is the recipe divided by the temperature at which that system exists in that reversible process, right. So, this is the recipe to calculate change in entropy. Okay. So, this is the definition of change in entropy according to second law of thermodynamics. Okay. Sorry, this is still not second law of thermodynamics, this is just a recipe to calculate change in entropy. ds equal to delta q reversible, I should do a quasi static process like I am doing here, divided by the temperature, right. So, at any given temperature I am exchanging a teeny little bit of heat with the surrounding, right. So, how much heat did I lose or how much heat did I gain from the surrounding, right, that defines the sign, tells me how much entropy have I increased. If I am gaining heat, I am actually able to, my molecules are able to access more states, more energy states, and so my entropy increases, right. If I am losing heat, the number of available states can reduce, and so I am losing entropy, right. So, that is what this means. Okay. Now, in this case, system is losing its heat to surrounding, right. So, SA, right. So, we said SA, right. So, I start with system A is less than SB, right. But all this, right. So, it is losing heat in a very slow fashion, right. So, delta Q into the system is equal to minus delta Q into the surrounding, right. So, whatever system is giving, surrounding is taking it. So, as a result, delta Q system by T is equal to delta Q surrounding by T, right. I can integrate this and I get that the change in entropy of the system, which is equal to SB minus SA, is equal to minus the change in system of the entropy of the surrounding, that is equal to surrounding, right. So, SB bar S surrounding delta S system, correct. So, whatever is the change in entropy of the system, the opposite is the change in entropy of the surrounding, right. So, in this quasi static process. So, if I look at the total ds, ds of system plus surrounding, that is ds of A, sorry, or total ds, right. So, let us just look at the total ds of system plus surrounding is equal to 0. Okay. In process 1, ds total ds, this is ds of the universe or system plus surrounding, is greater than 0, this is total. In process 2, ds total is equal to 0, right. I combine these two and say second law of thermodynamics, okay, which tells me how to calculate this ds. This ds is delta q reversible by T. It also tells me that ds is greater than or equal to 0. Always the entropy should be increasing, right. And when if I look at entropy of the system as a function of time, right. So, the entropy keeps increasing, and then eventually when the entropy saturates, here the ds equal to 0, right. So, here ds is greater than 0, then I define this is where the system has achieved its equilibrium with the surrounding, right, or the system, and sorry, this is for the universe, entropy of the universe, not the system per se. Entropy of the universe will always keep increasing, right, and the universe is in equilibrium, which means every system is in equilibrium with every surrounding in the universe only if this ds tends to 0, right. So, and it also says that all systems tend towards equilibrium. So, it tells me the path towards equilibrium, right. So, second law of thermodynamics right gives us a path towards equilibrium, right, and all systems, I said you take the system away from equilibrium, taken away from equilibrium, all by, again I should I should be very careful here, this is all systems, and by system plus surrounding taken away from equilibrium will come to equilibrium by generating entropy, right. So, here entropy is being generated, total entropy is like money, right. So, there is always inflation, it is not a conserved quantity, it is always generated, right. So, entropy is inflated, and at the end entropy goes towards equilibrium, which means so the system has come to an equilibrium, that is my dead state or the equilibrium state. Okay. So, again a lot of things to unpack here. So, ds, first of all I have a recipe to calculate ds, I have to go to a reversible process and then calculate ds as delta q reversible by T. Having said that, ds can also exist for non-reversible processes, right. It is not it just does not exist for reversible processes, it also exists for processes which are which go through some kind of a non-equilibrium or non-quasi static, right. So, for example, our process 1, where I have just broken this barrier suddenly, right. So, once I suddenly break the barrier, initially the system is in equilibrium with the surrounding, right. So, this is an equilibrium system. Suddenly I break the barrier, all this gas is gushing out, that gushing out period, that spontaneous gushing out is not equilibrium, right. I am not calculating anything while the system is coming out, right. So, if I actually say that, okay, so if I define a couple of states on this what is called an equilibrium plane, my system A is here, right, it has to go to system B on this plane, right. Now, in a quasi static process, I am actually, this is what is called an equilibrium plane, I can imagine it like this is an equilibrium plane. In a quasi static process, my equilibrium is actually going from state to state to state, every time so I am at equilibrium, I am in this equilibrium plane, right. So, every time I move my piston a bit, I am going to this state, then I move my piston a bit, I move to this state, then I move my piston a bit, I move to this state, right. So, every time I can define state variables, right, and it is in an equilibrium state. Now, you have to calculate entropy, you have to do this process to calculate the exact entropy, right. So, to calculate SB minus SA, I have to do this process and say SB minus SA is delta Q reversible in this process, green process, divided by T. That is how I calculate entropy. However, that does not mean if I do another process, right. So, where I suddenly break the barrier and then the system is the gas is gushing out. Once the gas is gushing out, there is no way to stop until it reaches its equilibrium, right. In that process, that is a non-equilibrium process. While the gas is gushing out, I do not care about what is the temperature of the system, I am not defining anything, right. However, the initial system is system A and then it goes out of equilibrium, which means it is going out of this equilibrium plane and eventually coming back to the B system, SB, right. Now, here I do not have a recipe to calculate SB minus SA, right. SB exists, SA exists, but the only way I can calculate SB minus SA is to go back to a quasi static process, and then say however the system may go to SB from SA, it does not need to be quasi static. Since I calculated this for a quasi static process and since entropy is what is called a state variable, the SB minus SA calculation remains the same, right, as done for a quasi static process. Okay. But so in this case when I am doing this out of equilibrium plane thing, I look at the entropy of the universe, and universe is entropy of system plus surrounding, that is still less than 0. Oh sorry, so the entropy increases, that is greater than 0. Okay. So, that is delta S when the system is in B state minus S when the total system plus surrounding is in capital B state minus S when the total system plus surrounding is in A state, that is greater than 0, right. This means that the system is still in an it is going through a non-equilibrium pathway, right. In other words, if ds is greater than 0, something is already happening, right. So, it evolves, this is out of equilibrium, right, and it goes in the path which takes ds equal to 0. Okay. So, this is equilibrium, right. If I take a system and slightly distort it from equilibrium, and ds means ds of the universe, right. So, this we will start appreciating when we look at closed systems, but ds of the universe, right. So, second law of thermodynamics tells me that the ds of the universe for non-equilibrium, when things are in non-equilibrium with each other, that is always increasing. Where is it increasing to? It is increasing to a state where ds equal to 0, that is it is always going to an equilibrium state, right, which means all the dynamics are actually happening in your while the system is going towards equilibrium. All the dynamics, right, that is evolution of system from one state to another state are happening while ds is greater than 0, or while so in this plot S versus T, right, this is of the universe, this is where all the dynamics are happening, right. So, we take system slightly away from equilibrium, that is perturb them, right. So, because we want to do everything in a linear regime and then let them go towards equilibrium and then see how these dynamics are evolving. Now, this dynamics can be just mass growth, that is your thin film growth. This dynamics can be some kind of polarization switching or magnetization switching or some phase transitions that are happening, right. all these things are happening because I am changing the equilibrium, or so I am making this ds term greater than 0, right. You can imagine that to be going from one state at a particular equilibrium to another state which is at another equilibrium, right. The pathway that I follow, it can be completely non-equilibrium, that is okay. I still define my SB and SA, right, but delta S overall should be greater than 0, only then I can go from SB to SA. In any process that I am doing, the total delta S should be greater than 0, okay. Unless I do it very quasi-statically, then the maximum limit, the minimum limit I have on delta S is delta S equal to 0, okay. Okay, so that is the second law of thermodynamics. It tells me a recipe of how processes go towards equilibrium. What is the quantity, what is the mathematical quantity that I need to look at, I need to calculate so that I can predict this process, right. I do not so first of all I need to understand what is equilibrium, and secondly I take the system slightly away from equilibrium and calculate the total delta S of the universe, right, and then see how this delta S is evolving, and thus that evolution tells me how my system is going towards equilibrium, okay. Okay, so let us stop this here, but tomorrow in the next class we are going to take this up further for what are called closed systems, okay, and open systems actually follow. And in closed systems, because so far I have been saying delta S of the universe is greater than or equal to 0, that is a recipe for systems to go towards equilibrium, or systems plus surroundings together to go towards equilibrium. But so my interest is in the system, my interest is not in the surrounding, right. So it will be nice to reframe this, right. So reframe this second law of thermodynamics statement, keeping in view that all I care about is my system, not the surrounding, right. So I can measure, I can fix the temperature of the system, I can fix the pressure in which this system exists, right. So all the chemical reactions or whatnot I want to see in my material growth are happening in the system, right. I do not want to know, what is happening to the surrounding. I mean, how many molecules are there in surrounding, how many states have changed in surrounding, right. The details of surroundings are not that pertinent for me, right. I want to dump all the details of surrounding in some temperature, some pressure or something, and I want to just care about the system, right. And in that sense, if I am doing that, right, and then I want to say this system is moving even now, right. So you see that I have been having trouble saying that system is taken away from equilibrium, but the entropy of the universe is changing, right. So I do not want to care about the universe, I just want to care about the system, right. So can I rephrase this second law of thermodynamics in such a way that I only care about my system of interest, all the surrounding parameters are dumped in certain things that I can measure or I can calculate, and then I get a recipe for when processes happen, when spontaneous processes happen or when spontaneous processes do not happen, right. So that is, does barium carbonate react with titanium oxide to give rise to barium titanate, how spontaneous is this reaction, right, at a certain temperature and pressure, is something that I do not want to care about what is happening to the water molecules outside, what is happening to the entire other universe. I just want to care about what is happening to barium titanate plus titanium oxide. Is this a spontaneous reaction? When can I say that this is actually going to give me barium titanate, okay, under what conditions, right. So and is it a feasible reaction or not a feasible reaction, right. So to ask, or water converting to ice, I just want to consider water and ice as my system. I do not want to understand what is happening in the because water is converting to ice, some temperature of the air near this vessel has changed, and so the surrounding is also changing. All these things, the surrounding information is useless for me, right. I do not want to pay much attention to that. I just want to understand the system of interest, like sharp focus on the system of interest. And for that, so we will see that so if I bring system into focus, I start defining newer thermodynamic potentials, right, derived from entropy, of course, right. So I start defining newer thermodynamic potentials like free energies, the so called Helmholtz free energy, Gibbs free energy, and so on and so forth, and we then give our the direction of spontaneity, right. So this is, if you have here in this case delta S of universe is greater than or equal to 0, that is when things are proceeding further, right. So, in that sense, can I define these other free energy functionals just for the system and say that something like delta G of the system is less than or equal to 0, then or less than 0, then the system is actually moving in the direction where where delta G goes to 0, right, in the direction of equilibrium. The system is moving. So, system is taken slightly away from thermodynamics, but I know the pathway in which it is moving, right, and I can use this pathway to do things of interest to my system. Okay. So, we will define these potentials in the next class, and so it all comes from the second law of thermodynamics. Okay. All right. So, with that, let us finish this here, and I will see you in the next class. Thank you.